Folks looking at class 68, our goal is to find the relationship between wavelength and frequency. So, a little situation here, your classmate creates a standing wave by moving her hand up and down 10 times in a span of 4.5 seconds. What is the frequency of the wave she is creating? So, real easy. Um, Finding the frequency. So, there's no formula for frequency in your reference table unless you have the period. But we know that by definition, frequency, I'm going to write this out, frequency is equal to number of oscillations over time. So it's not really an equation that you would ever be given, but it's just an idea to know. So we have 10 oscillations over 4.5 seconds. So the frequency she's creating is about 2.2 hertz. All right. And if you wanted to find the period is one of the frequency. So you can find that out just for extra practice. All right. So here's another little activity. So let's say this is a standing wave on the right, 4 different standing waves. So what we could do here is find the wavelength of each one. Now this is a lambda. This is the symbol we use for wavelength. All right. So let's find the wavelength of each wave. Now, the wavelength of each one, you might be thinking, oh, it's 3 meters because it's listed there. No, a wavelength is the length of one full wave cycle from either node to node or the distance between, I guess you could say 3 antinodes. From one antinode, skip one and then another one. Two non-successive nodes is what some people say. It's a little more confusing though. So let's kind of look at this right here. Let's see. The first picture here we have, let's see, how many wavelengths is that? That looks like half of a wavelength, okay, because it's just like one crest or one trough. So this is half of a wavelength, okay? So how do we get the total wavelength? Well, you might be saying, okay, well, that's half a wavelength, so the total wavelength is 6 meters. Well, it's not always going to be that easy. So what's like a formula we could use? Well, we know that we have 3 meters over half a wavelength, so that's 6 meters. All right. Over here, it looks like we have one full wavelength. So this is one wavelength. Okay, so 3 meters over one wave, we're going to have 3 meters is our wavelength here. So, and that kind of makes sense. It looks like a shorter wavelength anyway. All right, let's check out this next one here. This looks like, let's see, one wave and then an extra half wave. So this is 1.5 wavelengths. So if we have 3 meters total, 1.5 wavelengths, this is going to be 2 meters. So we have 2 meters there. And the last one, let's see, this is one wave. This is 2 waves. So we have 3 meters over 2. 1.5 meters is our wavelength. Think about that for a second. Like this distance here of one wavelength is half of this 3 meter distance. So that kind of makes sense. All right, so we watched the video. You can read through the directions, check out the video that's associated with class 68. And we took some data. And these wavelengths happen to be the exact same wavelengths that we saw up here at the top, okay, because the length of the rope was 3 meters. All right, so these are the frequencies that your groups found. I just took one of the groups. So we can't really go through all this right now in the video, but you kind of get the idea. So what we did was we graphed frequency versus wavelength, or you could have done wavelength versus frequency. You would see the same relationship. We actually see an inverse relationship. This is not a negative linear relationship. This is an inverse relationship. Okay, as one goes up, the other goes down, and they both asymptote at 0. That's an important point. Like neither one will ever hit 0. All right, so this is an inverse relationship reasoning because as wavelength got bigger, frequency got smaller, and vice versa. Look, as wavelength got smaller when we went down, the frequency got bigger as we went down. Or as wavelength gets bigger as we go up, the frequency got smaller. All right. And this is just what an inverse relationship looks like. If we had more data points, it would have been even more evident. All right, so quick question here. A wave generator produces straight parallel wavefronts in a shallow tank of uniform depth. As the frequency of the vibration of the wave generator increases, which characteristic of the wave will always decrease? So frequency goes up, wavelength must go down, all right, as we just saw.